Welcome back to Caesar Education. Now, let's talk about determinacy. We're still doing some structural analysis, but we have to get through some basic ideas first before we start analyzing some structures. Now, in engineering mechanics, in physics, and in mechanics of engineering, we said that for a structure or a member to be in equilibrium, we need all the forces to be equal to 0, and we need all the moments about some origin O to also be 0. Now, these two equations of equilibrium are sufficient and necessary for a member to be in equilibrium. If all the forces add up to 0, that means all the forces are in balance. We say that this is a balance of forces. When all the forces are in balance, they will add up to 0. Therefore, your member will not move in a certain direction, and will either be still or will have no acceleration. Now, with moments, when a member's moments add up to 0 about some origin O, we say we have a balance of moments. Now, remember that a moment is when some certain force is exerted on a member and tries to bend it. So another reaction will prevent it from bending, therefore causing a moment at that reaction. Now, if all the moments are balanced, that means there will be no bending in your member. Now, if these two equations for forces and moments are equal to 0, then your structure is adequately in equilibrium. Now, if you have equations, then you're gonna need parts of the structure. You're gonna need forces from the structure that you are going to substitute in your equation. Now, if your member has more forces than the equations that you have, let's suppose the forces your unknown forces are 3, but you have 2 equations, then you will know that, okay, I do not have enough equations to solve for my unknowns. And if that is the case, we say that your member is statically indeterminate. And that's what determinacy is. It's basically checking whether all your unknown forces, you have enough equations of equilibrium to solve for your unknown forces. So usually there will be 3, whereby you have the x component of the forces, the y component of the forces, and the moment. Usual, but sometimes you may have another plane, a third plane that will give you an extra equation. Now, if you have 3 equations but your unknown forces are 4, then your structure is statically indeterminate, meaning you cannot work out the unknown forces and your structure might have some imbalances. Now, if you have 3 equations and you have 3 unknown forces, the number of forces are equal to the number of equations, then your structure is determinate. And that is what determinacy is. You take your structure, you look at the amount of equations that you have, and then you look at the unknown forces on your member, and that if they are equal, you have enough equations to solve for your unknown forces, then your structure is statically determinate. But if you have more unknown forces than the equations of equilibrium, then your member is statically indeterminate. So one way that you can do this is by drawing a free body diagram, counting all the forces, and then counting all the equations that you have, and then determining whether you have enough equations for your unknown forces. For coplanar forces, you usually have three 3 equations of equilibrium. Equations of equilibrium. With the 3 equations of equilibrium, you are going to assign them to each member, each part that you have in your element. Now, this one that I have here only has one part, so I would just have use 3 equations. If I had 2 parts, then I would assign 3 to each part, which means that I would have 6 equations. So that is to tell us that to find how many equations that we are going to use, we are going to multiply the number of parts by 3, and that gives us 3n, where this n is the number of parts in your element. Now, like I said, this is just one part. If there were 2, I would multiply it by 3 because my n will be 2, because n is the number of parts. And then after, we are going to represent our forces with R. And now say, okay, I have forces and I now have the number of equations, which is the number of parts times 3 in coplanar forces. And are they equal? Now, if the number of forces is equal to 3 times the number of parts, because we are going to assign all the 3 equations to each part, then your member is statically determinate. Statically determinate. Now, if they are not equal and you happen to have more forces than the number of equations, then your structure is statically indeterminate. Now, these 2 equations, you can use them to check if your structure is determinate or not. Now, we say that R is the number of forces and n is the number of parts, and we multiply n by 3 because we are going to take the 3 equations of equilibrium that we have for coplanar forces and assign it to each member. So if you have 4 members, then each member will have 3 equations. Therefore, we multiply 4 by 3. Now, if the number of unknown forces is equal to the number of parts, then you know that number of equations, then your structure is statically determinate. But if there are more unknowns than the equations, then your structure is statically indeterminate. Now, let's look at this member that I have here and see how many forces do I have here. Now, we already know that we only have one part, so n is 1, and 3 times 1 is equal to 3, because we take 3 and multiply it by n, and n is the number of parts, and we only have one part here. Now, how many unknown forces do we have? To find the unknown forces, we look at the reaction. There's no other external force acting here. We only have the forces from the reactions of the support. Now, at A, we have a roller, and you know that a roller allows translation in the x-axis, but it supports the member in the y-axis. So we'll have a reaction there, AY. So your beam, maybe let's say this is some sort of floor. The beam that supports your floor will have a reaction at A, and that reaction will be in the y-axis, because a roller supports your member in one axis. Now we also have a roller at B, and if you have a roller at B, that means that it will be supported only in the y-axis. So we have BY. This B will allow translation in the x-axis but not in the y-axis. You can intuitively see that if gravity is acting on this member, this reaction is stopping it from going down. Therefore, the reaction is acting in that direction. Now at C, we have a fixed support, meaning that our member is embedded into the wall. Now if it is embedded to the wall is stopping our member from falling down, which means we have a reaction in the y-axis. We'll have a CY. And also, if you try to pull this member to the right or push it to the left, this wall will also be holding it fixed. We call it a fixed support. Now it will be holding it so that it doesn't go to the left or to the right, meaning that we also have a reaction in the x-axis. Therefore we have a CY. Now if this B and A were not there and this member was trying to bend, this wall is holding it in a fixed position that it doesn't bend. The same thing as if I hold this pen and I say, okay, I'm trying to push it down and my hand is holding it so that it doesn't bend. The same thing will happen at this fixed support, meaning that at this fixed support we'll also have a moment at C. Now these are all our unknown supports, meaning that our R is equal to 1, 2, 3, 4, 5. Now we go back and say, okay, we say that R, we compare it to 3n. Now the number of forces, which is R, is 1, 2, 3, 4, 5. And 3 into the number of parts, we have 1 part here in our member, therefore it's 3 into 1, which is 3. Now we have more unknown forces than our equations. 3 times n gives you the number of equations. So 5 is greater than 3, therefore R is greater than 3n. And we say that if R is greater than 3n, your structure is statically indeterminate. Now, when a structure is statically indeterminate, I'm not necessarily saying it will be unstable, but to find the unknown forces, you will have to find some other equations, because we have 5 unknowns and 3 equations. So you would need 2 extra equations that will solve for your unknowns. We call that those compatibility equations, but that will come later in the course. Maybe in your textbook you'll find it in chapter 10, and we are only at chapter 1 now. Now the difference between 5 and 3, the difference between the number of forces and the number of equations. Now I'm saying R minus n, it will give you the degree of indeterminacy. Now this structure is indeterminate, right? Now to what degree? It will be 5 minus 3, which is 2. Now the number of equations that you are missing, we call it the degree of indeterminacy, and that's how many extra equations you will need, or extra compatibility equations that you would have to find, so that you can make sure that your member is stable. For here I was dealing with a beam, and now let's just try with some pin supported members. Now this member is one fixed member, so it is one fixed member that is supported on 2 sides. Now on one side it is supported with a roller. Now when you have a roller, we know that this roller allows translation in the x-axis, but it supports it in the y-axis, and it will support a reaction. Let's say here it's A, therefore we'll have AY. And here again you have a pin support here, meaning that this member is pinned to this support. Now this support, it can allow rotation. This pin, you can see that it can allow some rotation, but it won't allow this member to either go up or down. So there's a reaction here, let's call it B, which is BY, and it won't allow it to go to the left and right, because you can see that it's pinned to the floor, so it cannot move left or right, up or down. So there will be a reaction in the x-axis also, and we call that bx. Now that we know that our r is equal to 3 because we have 3 unknown forces. Now in this case, I'm not cutting it open here because it's it is fixed here, so there's no need to cut it open here and check for internal reactions. It is just one joint member, meaning that n is equal to 1. Now let's compare the number of forces to the number of equations. We said that our r must be equal to 3 times n. Our r is 3 and our n is 1, so we'll have 3 equal to 3. Now our condition holds that r is equal to 3n. 3 is equal to 3, therefore this structure is statically determinate. Now let's move on to the following example. Now we just follow the same procedure for all our members. We look at the supports, count the number of unknown forces and compare them to the number of equations. Now in this member, this is more complicated than the previous ones because there's a hinge here in the middle. Now if there's a hinge here, that means these two parts are joined together by this hinge and are not one solid part, and this joint here is not fixed. Therefore, now we are going to separate the two parts. We already know that our n is equal to 2 because we just said that we have part 1, which is this one, and part 2, which is this one. So our n is equal to 2. What about our r though, which is the number of unknown forces? So what we are going to do is to take each part. Let me just draw an ideal. These lines represent each part, so these are the ideal structures, and just draw it like this. And now look at the supports here. Now we have a member that is being pushed towards the wall. Now if we look at the support, we have this support is called a slider, and a slider has 2 reactions. It supports our member in the x-axis. I forget to name this part, A, B, and C. Now it supports this member in the x-axis, so we'll have AX, and it also supports makes a moment. It will be very important that you know the type of supports that you are dealing with and what type of reactions they have. So this may look like a roller that is in the y-axis, but it is actually called a slider, and it will have a reaction in the x-axis and a moment. Now at B, once you have a hinge here, a hinge can allow rotation, but it cannot allow movement in the x and the y axis. So let me draw them again here and say, here we have AX and we have a moment MA. Now here at the hinge, it will be supported in the x-axis, therefore you'll have a reaction BX, and you'll have a reaction in the y, which is BY, but it allows rotation though, so there's no moment. Also in member number 2, these same forces will be there. You will have BX and you will have BY. Now we are not going to count 4 forces here because the same BX that is acting on this member is the same BX acting on this member. The same BY on this member is the same BY because of the Newton's third law. Now At the end of the second member, we have a pin, and we know now that a pin supports in the x-axis, so we'll have cx and we'll have cy. They are two unknown reactions at a pin. It allows rotation, so there's no moment. Now let's count the number of unknown forces. We have 1 moment, 2 ax, 3 by, 4 bx, 5 cx, and 6 cy. So our number of unknown forces is 6. Now we go back to our equation of r equal to 3n, and we compare. Now the number of forces, unknown forces, is 6, and number of parts is 2. So 6 equal to 6. That means the number of forces is equal to the number of equations. 3 times the number of parts is the number of equations. Therefore, this structure is statically determinate. So now this last example should be easy for everyone. We have 2 hinges, 1 and 2 here, and we have 3 parts, 1, 2 and 3. So we already know that our n is equal to 3. Now we just need to find the reactions at the supports. Now for member 1, it has a fixed support on the side, and at a fixed support we'll have a reaction in the y, we'll have a reaction in the x, and we'll also have a moment. Now on the side of the hinge, a hinge allows rotation, so there's no moment, but there is a reaction in the y-axis and the x-axis. Now on member number 2, we have it has hinges on both sides. So on the side it will have x-axis reaction in the y-axis. Also on the right hand side it will have a reaction in the x-axis and a reaction in the y-axis. Now the last member number 3, on the left hand side it has a hinge, so we'll have a reaction in the x-axis and a reaction in the y-axis. But on its right hand side it is connected to a fixed support. It is fixed into a wall, so we will have a reaction in the x-axis, the y-axis, and the fixed support does not allow rotation, so we'll have a moment. So how many unknown forces do we have? What is our r? Now we'll count moment 1, 2, 3, 4, 5. Now before I continue, remember that here where these members are connected by a hinge, these forces are the same. This x-axis force reaction on member A is equal to this x-axis reaction on member B because of Newton's third law. So they will be equal, or else this support will not be in equilibrium, or it will not be stable. So we'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So our number of unknown forces will be equal to 10. Now let's find 3 times n. Our n is 3, therefore it is 9. Our r though is 10, therefore our r is greater than 3n. We have more unknown forces than equations. To what degree? The first conclusion we make is that because we have more unknown forces than equations, that means that our structure is statically indeterminate. Now on top of that, to what degree is it indeterminate? If we have 10 forces, 9 equations, it is indeterminate to the first degree. 10 minus 9, it is 1. So we only need one extra equation. And I said that we'll discuss compatibility equations later on.